By the end of this video, you're going to be able to draw this, every box. And more importantly, you will be able to say why each one is there and what it cost us to add it. Right now though, none of it exists. Today, our app is one computer that costs about 800 rupees a month. And in roughly 4 minutes, it's going to catch fire. Here's the thing nobody tells you at the start. There are dozens of tools out there. Databases, caches, load balancers, queues, CDNs. Learning what each one is, that's the easy part. You could read all the definitions this afternoon. The actual skill is knowing which of them you need, where to put it, and what it costs you to add. That's system design. Choosing the right pieces and putting them in the right places to solve a real problem. And it's the thing that quietly separates engineers. Early on, you're handed a feature. Here's the input, here's the output. Go build it. Later, you're handed a problem, and you figure out the approach yourself. Eventually, you're handed a blank page, and you decide what the whole system should even look like. We're going to practice that last one. And we're going to do it the only way that actually works. Not by listing components, but by building one real app and watching it break. So let's build it. Two friends have an idea. A food delivery app. Order from restaurants near you. They call it Dabba. They write the code. And now they need somewhere to run it. So they rent a server. Now, a server is not a special magical machine. It's a computer. Same parts as your laptop. A processor, some memory, a disk. It just lives in a rack in a data center instead of on a desk. It has no monitor plugged into it, and its entire job is to sit there and answer requests all day. And there's a second meaning of the word, which is worth getting straight now. A server is also the program running on that computer. The one that's listening on a port, waiting for someone to talk to it. Both meanings are correct. People use them interchangeably, and it confuses everybody, so the machine and the program listening on it. And this costs them about 800 rupees a month. That's not a made-up number. That's genuinely what a small cloud machine goes for. So where does everything go? On that one server. All of it. The app itself, the database holding users and restaurants and orders, even the photos of the food. And I want to be really clear about this because it gets sneered at. This is a good setup. For where Dabba is right now, it's the correct answer. It's simple to build, it's simple to deploy. And when something goes wrong, there's exactly one place to look. Most apps should start exactly like this. And a lot of them should stay like this for years. 200 users, 40 orders a day. Everything is fine for about 3 weeks. Hard cut to silence on for about 3 weeks. Then a food blogger posts about them. And on a Friday evening, 10,000 people open Dabba. Now every single one of those people is doing work on that one machine. The app is running database queries, resizing restaurant images, checking logins, all on the same processor at the same time. And here's what that actually feels like to a user. A page that used to load in 200 milliseconds now takes 10 seconds. Nobody waits 10 seconds for a food app. They close it and order from somewhere else. So the app is broken. But broken isn't one thing. And this is the part that matters. There are 3 completely different ways this one box is failing right now. Each one has a name and each one has a fix. And honestly, that list of fixes is basically the entire field of system design. Beat of near silence as the users peel away. Failure 1. The machine runs out of processor and memory. There's simply more work arriving than one computer can do. The obvious fix is to get a second machine and send half the people to each one. But the moment you do that, you've created a brand new question. When someone opens Dabba, which of the 2 machines should they talk to? Somebody has to stand at the door and decide. That someone is called a load balancer. Think of a restaurant with several identical kitchens and a waiter At the door, sending each diner to a free one. That's the first box we're adding. Failure 2. The database is answering the same question over and over. Most of those 10,000 people are asking for the same handful of things, the same popular restaurants, the same trending dishes. And the database works out the answer from scratch every single time. The fix is to keep the popular answer sitting somewhere fast so you stop asking, like printing the menu once and putting a copy on every table instead of walking to the kitchen to ask what's in the biryani. That's a cache. Box number 2, failure 3, and this is the frightening one. The machine just dies. A disk fails, a power supply gives out, somebody unplugs the wrong cable, and because everything lived on that one box, the app, the database, every photo anyone uploaded, all of it is gone at once. That has a name, a single point of failure. The fix is to stop keeping things in one place. Keep a live copy of the database on a second machine and move the photos out to storage built specifically for holding files safely. Now look at what we just did across those 3 fixes. We didn't rewrite the app, we didn't make the code cleverer. All we did was decide where the pieces live. That's system design. And every single fix we just added brings a problem of its own. The load balancer can die too. The cache can start serving out-of-date answers. The copy of the database can fall behind the original. Fix something, get a new problem. Fix that. That chain is the rest of this video. One quick thing before we go further, because you'll hear these 2 terms constantly and they trip people up. High-level design is the zoomed-out view. The big pieces and how a request moves between them. The app servers, the database, the cache, the queue. Where does a request go? Where does data live? What breaks first when traffic grows? Low-level design zooms all the way into one feature. Say, the rate this order button. Which function handles the tap? How do we stop the same person rating twice? What exactly do we write to the database? Same system. 2 completely different altitudes. This whole video lives on the left. We're going to talk about components, how they connect, and what each choice costs, not the code inside any one box. So the instinct now is to start drawing boxes. Resist it for 4 more minutes, because there are 2 questions you have to answer first. And they are very different questions. The first one, what should the app do? The second one, how well must it do it? The first is called a functional requirement. The second is a non-functional requirement. You'll also hear those called quality requirements, which is actually the term the international standard uses. And that difference sounds like textbook nonsense right up until you see what each one actually does to your design. No chime. This scene is set up. Functional requirements for Dabba are the easy part. Just list what a user can do. Browse restaurants nearby. Place an order, pay. Track the delivery. Rate it afterwards. Every one of those is a feature you can point at and test. Either placing an order works or it doesn't. If one's missing, the app is incomplete and everyone notices immediately. Non-functional requirements are different. They're not features, they're qualities. The order goes through, but does it go through in half a second or 8 seconds? The payment succeeds, but does the record survive if a disk dies? It works for 100 users, but does it still work at 8 o'clock on a Friday with 100,000? Nobody can point at a non-functional requirement in a demo, but everybody feels them. Now here's the part that makes this worth stopping for. Take a food app someone builds for their neighborhood and take Swiggy. Write out the feature lists. Browse, order, pay, track, rate. They match almost line for line. The functional requirements are the same. What makes them completely different systems is entirely non-functional. One serves 50 people who'll forgive a slow evening. The other serves millions who leave after 2 seconds. And that tells you what the rest of this video actually is. Every component we add from here, the waiter, the menu, the copies, the shelf, None of them are features. Not one user has ever asked for a cache. Users ask for a fast app. The cache is how you give them one. Beat of silence. As the identical feature lists sit there. So before drawing anything, you ask 5 questions. These 5 shape every decision that follows. A food app with 1,000 users and one with 50 million are not the same system. For Dabba, we'll say we have 10,000 users today, and we're roughly doubling every few months. So we design for the millions we're heading toward, not the 10,000 we've got. Think about what people actually do on Dabba. They open it, scroll restaurants, look at menus, check a few dishes, and maybe order once. Scrolling and browsing is reading, placing an order is writing. So Dabba is overwhelmingly read heavy, which means the reading path, the browsing, the menus is where the effort should go. Someone's placed order and their payment? Never. Lose that and you've lost a customer permanently, and possibly a legal problem. But the little trending near you count being slightly stale for a minute, nobody will ever notice. Knowing that difference tells you exactly where to spend money and where to relax. Opening the app and seeing restaurants has to feel instant. Call it under 200 milliseconds. But placing an order, people will happily wait 2 seconds because placing an order feels like it should take a moment. So we can afford slow, careful work on the ordering path, and we absolutely cannot on the browsing path. Every extra machine, every copy of the data, every cache, that's a bill every month, forever. The right design isn't the one with the most boxes, it's the one that satisfies the first 4 answers for the least money. Now, one bit of arithmetic. It takes 90 seconds and it will tell us something genuinely surprising. Say 1 million people have installed Dabba and 100,000 of them open it on a given day. Each of those opens it about twice and pokes around 20 screens per visit. That's 4 million requests a day. Divide by the 86,400 seconds in a day, and you get about 46 requests per second. Call it 50 a second. That is not very much. One decent machine handles that. But traffic isn't flat. Nobody orders dinner at 4 in the morning. It all lands in the same 2 hours. So at the dinner rush, we're maybe 10 times the average. 500 a second. Rough multiplier. You'll hear anywhere from 2 to 10 times used. The point is to size the spike, not to be precise. Now storage. 50,000 orders a day and an order record is about a kilobyte. The items, the address, the amounts. That's 50 megabytes a day. Call it 18 gigabytes a year. 18 gigabytes. That fits on a laptop. That's nothing. Now the restaurant photos. 20,000 restaurants, 30 dishes each, and a photo is around 400 kilobytes, 240 gigabytes. And every one of those has to be delivered to a phone over and over all evening. Look at what that just told us. We haven't drawn a single box yet, and the arithmetic already knows where the pain is going to be. It isn't the orders, it's the images. Hold on to that. It comes back. 3 words you need, because people mix them up constantly. And they're genuinely independent. A kitchen can be serving a huge number of people while every individual person waits 40 minutes. High throughput, terrible latency. Now the third one, and it's the one that actually matters in practice. When you measure how long requests take, you don't get one number. You get thousands, all different. So people quote the middle one, the P50, the typical experience. Half of requests were faster, half slower. Fine. But the average is a bit of a liar. Because look at the far end. Line up 100 users by how long they waited. The 99th person, that's your P99. And on Dabba right now, while the typical person waits 180 milliseconds, that person is waiting 4 seconds. The average said everything was fine. 1 in every 100 people is having an awful time. And at 500 requests a second, That's 5 people every second deciding your app is broken. Last one, and then we start building. Availability. How often the app is actually up? It gets written as a run of nines, and the nines are deceptive. 99% sounds excellent. It's 3.5 days of downtime a year. Add a 9, 99.9, and you're down to about 9 hours. Another 9, 52 minutes, and another 5 minutes. For a whole year. Each 9 you add divides your downtime by exactly 10, and each one costs dramatically more than the last. But here's the number I actually want you to remember, because it's the reason for half of what we build later. Amazon publishes a guarantee for its cloud machines. Across a whole region, they promise 99.99%. For a single machine, they promise 99.5. 99.5% is 1.83 days of downtime a year. That's not a small or print detail. That's the cloud provider telling you, in writing, that one machine is not allowed to be reliable. The only way to get those extra nines is to stop depending on any single one. And that is exactly the problem we're going to spend the next hour solving. Beat of silence on 1 to 83 days, year. So we need more machines. That much is settled. But before we start making copies of Dabba, we should probably agree on what Dabba is. Because run 10 copies of the app means something very different depending on how the app is built. Right now, Dabba is one program. Sign up, browsing, ordering, payments, ratings, all of it lives in one code base, and it gets deployed as one thing. Everything inside can call everything else directly. It's just a function calling another function in the same program on the same machine. Nothing in between. That's a monolith. One code base, one deployment, one thing running on your servers. And it has one property worth noticing. Change the sign-up page, and you redeploy the entire thing. The alternative is to split that one program into several separate programs. A service for browsing, one for orders, one for payments, each with its own code base, deployed on its own, running on its own machines. That's microservices. And because they are now separate programs on separate machines, they can't just call each other. They have to talk over the network. Hold on to that last sentence. It's the whole trade. No chime. The payoff is the next scene. Now, there's a story going around that microservices are what real engineers use, and a monolith is something to be embarrassed about. That's just not true. But there are two genuine reasons to split, and they're both worth understanding. Remember what we worked out? Dabba is read heavy. People browse constantly and order occasionally. So browsing might need 10 machines worth of capacity, while payments needs one. In a monolith, you can't scale just the browsing. The whole program is one unit. So you scale all of it together. Want 10 machines for browsing? You just got 10 copies of the payment code too, sitting there doing almost nothing. Split browsing into its own service, and you scale exactly the part that's under load. When 40 engineers all deploy the same code base, they queue up behind each other. Someone's broken build blocks everybody. Give each team its own service, and they ship on their own schedule without asking permission. That's it. Those are the two reasons. Notice that neither of them is microservices are modern. They're both about a specific pain. One part needs different capacity, or one team is blocked by another. And the cost is real. Every one of those network calls can be slow, can time out, can fail halfway through. In a monolith, when something breaks, you read one log file. With microservices, one user tapping order might touch 5 services, and you have to piece the story together across all 5. So, which one does Dabba get? Today, with a small team and a few thousand users, the monolith, comfortably. And this isn't a beginner's compromise. It's the mainstream advice from the people who write about this for a living. Martin Fowler puts it about as bluntly as you can. Don't even consider microservices unless you have a system that's too complex to manage as a monolith. And there are some genuinely instructive stories of teams going the other direction. Amazon's Prime Video had a tool that monitors video quality on every stream. They'd built it out of separate serverless pieces and they hit a hard scaling wall at about 5% of the load they needed. So they packed the pieces back into a single process and cut their infrastructure cost by over 90%. Now, I want to be precise about this one because it gets wildly misreported. That was one internal tool, not Prime Video, the product, and certainly not Amazon. What they moved away from was a specific serverless setup, and the thing they ended up with still runs on many machines. They just cloned the whole program several times behind a router. It's a great story about picking the right tool and a terrible story about microservices being wrong. The second one, a company called Segment had grown to over 140 separate services, and the coordination cost was crushing them. They merged it back into one. Their shared code improvements went from 32 a year to 46. And there's a middle option people forget. Shopify runs one of the largest single code bases around. Thousands of developers, roughly 6,000 classes. And they deliberately chose not to go to microservices. They just enforced strict internal boundaries, a modular monolith. The honest summary comes from Amazon's own chief technologist. There is not one architectural pattern to rule them all. So Dabba starts as a monolith. Later in this video, when one specific piece gives us a specific reason, we'll split that piece out. And you'll see exactly what the reason was. Right. The app is one program and it's training. There are exactly two ways to get more power, and we should try the easy one first. The easy one is to make the machine bigger. More processor, more memory, a faster disk. This is called vertical scaling or scaling up. And it's genuinely a good move. You change nothing, not one line of code. You pay more money, you get a bigger machine, and the problem goes away for a while. If a bigger box buys Dabba another year, they should absolutely take it. But it runs into three walls. The first is price. Going from a small machine to a medium one is cheap. Going from the second biggest to the biggest can double your bill and give you maybe 20% more power. You pay more and more for less and less. The second is that there is eventually a biggest machine. Once you've rented the largest one that exists, that's the end of the road. And the third wall is the one we already know about. One big server is still one server. Make it as large as you like. If it goes down, Dabba goes down with it. Beat of silence on the 183 days tag returning. No chime. This scene ends unresolved on purpose. And that third wall isn't hypothetical. Here's how it actually shows up. 2:14 in the morning. The machine reboots to install a security patch. It's back in 6 minutes. For 6 minutes, Dabba did not exist. Not slow. Gone. Every order in flight failed. You cannot fix that with a bigger box. The only fix is to stop having one box. So, horizontal scaling. Instead of one enormous machine, run several ordinary ones, each with a copy of the app. Need more capacity? Add another. This is how every large system on the planet actually works. Because it gives you two things a bigger box never will. There's no ceiling, you can always add one more. And there's no single machine whose death takes everything with it. One of the 5 dies, the other 4 keep serving. But, and you probably saw this coming, the moment you have 5 machines running Dabba, you've created a brand new question. Someone opens the app. Which of the 5 machines answers? And a second problem, quieter but worse. Those 5 machines can't each keep their own copy of the data. If your order goes to machine 3 and your next app lands on machine 7, machine 7 has never heard of you. The data has to live somewhere all 5 can reach. Hold that thought. It's the next hour of this video. Beat of silence as the box goes dark. Let the 6 minutes sit. Before we answer which of the 5 machines, let's fill in something we've been skipping. Somebody opens Dabba and types dabba.in. What actually happens between that moment and food appearing on their screen? Every machine on the internet has an address, an IP address, a string of numbers that tells the network exactly where to deliver things. Think of it as the machine's phone number. But nobody types numbers, they typed a name. So the very first thing the phone has to do is turn that name into a number. That lookup is DNS, the domain name system. And the easiest way to think about it is the internet's phone book. The phone asks, "Where is Dabba in?" and DNS answers with the address. Now the phone knows exactly which machine to talk to. And this is worth pausing on for 1 second. Because it's the bit people find magical and it isn't. DNS is just a lookup. Name in, number out. That's all. No chime. The module payoff comes later. The phone has an address. Now the two of them need a language they both speak. That language is HTTP. The phone sends a request, essentially, "Give me the restaurants near this location." The server does the work and sends back a response, the list. Request, response. That's the whole shape of it. Every single thing you have ever done on the internet is that loop, over and over. But you'll almost never see plain HTTP anymore. You'll see HTTPS, and that S matters. Without it, everything between the phone and the server travels as readable text. Anyone sitting in the middle, someone on the same cafe Wi-Fi, can read all of it, including the password. With the S, that whole conversation is scrambled. It's the difference between sending a postcard and sending a sealed envelope. The person carrying it can see that something went past. They can't read a word of it. How that lock actually gets set up is genuinely interesting and entirely out of scope today, for now. The S means nobody in the middle can read your user's traffic. We already know latency, how long one round trip takes door to door. There's a second word that gets tangled up with it constantly, and untangling them tells us something about Dabba specifically. That second word is bandwidth. How much data you can push through at once. Latency is how long the trip takes. Bandwidth is how wide the pipe is. And here's why it matters for us. Open Dabba's home screen. It shows, say, 30 restaurant photos. Those photos are small. Bandwidth isn't the problem. A decent connection could move all of them in a blink. The problem is that if the phone fetches them one at a time, each one is a separate round trip, all the way to Mumbai and back. 30 round trips. Even on fast Wi-Fi, that's what makes the screen feel slow. Not the size of the data, the number of trips and the distance of each one. Hold on to this one too. Two of the biggest boxes we add later exist to fight exactly this. One that stops the trip to the database, and one that answers from a machine much closer to the user. Now we can answer the question we left hanging. 5 machines, 1 user. Who answers? Picture a restaurant with 5 identical kitchens all cooking the same menu. A diner walks in. You don't want them wandering around picking a kitchen. You want someone standing at the door who says, "That one, it's free." That someone is a load balancer. And the waiter is exactly the right picture for it. Its whole job is to take each arriving request and hand it to one of the machines behind it. Here's the part that surprises people. Remember DNS returning an address? That address doesn't point at any of your 5 machines. It points at the load balancer. Every request lands there first, and the load balancer decides where it actually goes. And the second surprise, a load balancer is not a special piece of hardware. It's a server running a program whose entire job is forwarding requests. There's a general name for anything that sits in front like this, taking requests on behalf of the machines behind it, a reverse proxy. A load balancer is the most common kind you'll ever meet. So when you hear reverse proxy, picture the waiter. So the full path now, the phone asks DNS for the address. DNS gives back the load balancer's address. The load balancer picks a machine. That machine does the work, and the answer travels back the same way. Every request to Dabba, from now on, walks that path. So how does the waiter decide? A few ways, and they're simpler than they sound. The simplest is round robin. Just take turns. First request to machine 1, next to machine 2, next to machine 3, and back round again. It's fine for a lot of apps, but it's blind. It doesn't know anything about how busy each machine actually is. So a smarter option is least connections. Send the next request to whichever machine is currently handling the fewest. The load balancer can do this because it's counting. It knows how many requests it has handed to each machine and how many are still open. And because machines aren't always the same size, there's weighted distribution. If two of your servers are twice as big, give them a bigger share. But the genuinely clever part isn't how it chooses. It's how it notices when something's wrong. Every few seconds, the load balancer quietly pokes each machine. Still alive? If machine 3 stops answering, the load balancer notices within seconds and simply stops sending it traffic. The other 4 absorb the work. And your users never see an error because the load balancer never sent them to the dead machine in the first place. That's a health check, and it's what turns a traffic splitter into something that actually keeps you online. One last thing, almost nobody writes their own load balancer. You use one that already exists. Nginx and HA proxy are the classic ones you run yourself, and every cloud provider offers a managed one. Which raises the obvious question, and I want you to have already spotted it. Everything now flows through the load balancer. So what happens when it dies? Same answer as always. You don't run one. You run at least 2. We'll come back to this properly because that pattern is about to repeat for every single component we add. Dabba is now running on 5 machines behind a load balancer. Traffic is spread nicely. And support starts getting a strange complaint. Users are being logged out. Not always, not predictably. They log in, use the app, and a minute later, it asks them to log in again, refresh, and they're back in. Refresh again, logged out. Nobody changed any code. So what's happening? Let's follow one user. Call her Priya. Priya logs in and that request happens to land on machine 1. Machine 1 checks her password and it's correct. So it makes a note. Priya is logged in and it keeps that note in its own memory, which is the completely natural thing to do. A minute later, Priya taps something else. New request. And the load balancer, doing exactly its job, sends this one to machine 4. Machine 4 checks its own memory for Priya. There's nothing there. That note lives on machine 1 and machine 4 has no idea machine 1 exists. So machine 4 says, the only thing it can say, who are you? Please log in. That's the bug. And it's not a small edge case. It is the single biggest thing that breaks when you go from one machine to many. On one machine, this worked perfectly because every request hit the same box. No chime. This scene is the problem, not the payoff. That note in machine 1's memory has a name. It's state, something the server is remembering between requests. And a server that keeps state is called stateful. The moment you put a load balancer in front of a fleet, stateful servers stop working. Different machines remember different users, and which one you get is basically a coin flip. So the fix is to make the servers stateless. A stateless server keeps nothing important in its own memory. It takes a request, does the work, sends the answer, and forgets you entirely. But Priya still has to stay logged in, so the note has to live somewhere, just not inside any one machine. You move it to a single shared place that all 5 can reach. Now it doesn't matter which machine gets the request. Priya logs in on machine 1 and the note goes to the shared store. Her next request hits machine 4. Machine 4 checks the same shared store, finds her, and she stays logged in. And that's the whole fix. But notice what it bought us because it's bigger than the login bug. The machines are now disposable. Add 1, kill 1, restart 1 for a patch at 2 in the morning. And no user feels a thing. That's why keep your server stateless is one of the first rules of scaling. Now there's another way to fix the logout bug, and you will absolutely hear people suggest it. So let's deal with it. You can just tell the load balancer, always send Priya back to the same machine. Pin each user to one server. They call these sticky sessions. And it works. The node stays on machine 1, Priya keeps hitting machine 1, nobody gets logged out. Cloud load balancers offer it as a checkbox. Amazon's, for instance, does it with a cookie that lasts anywhere from 1 second to 7 days. But look at what it costs you. It walks straight back into the problem you were running from. Priya is pinned to machine 1. Machine 1 dies. Priya's session dies with it, because the note was still only ever in that one machine's memory. You didn't solve the problem, you just made it rarer. And it breaks the load balancing too. The waiter can't spread traffic evenly anymore, because it's no longer free to choose. Some machines end up with all the heavy users. The specification that popularized stateless design puts it about as strongly as you can. Sticky sessions are a violation and should never be relied upon. And one clarification, because this trips people up constantly. Storing things in a database or in cloud storage does not make your server stateful. Those live outside the machine. Stateful means the server keeps something important inside itself. The question to ask is simple. If this machine vanished right now, would any user lose something? If yes, that thing shouldn't be living on the server. Let's pull back and look at what we've actually built. A user opens Dabba. DNS turns the name into an address. And that address points at the load balancer, not at any one machine. The load balancer picks a healthy machine out of the fleet, checking on each of them every few seconds so it never sends anyone to a dead one. Those machines are all stateless and identical. Any of them can serve any user, because the login sessions live down here in a shared store that all of them can reach. And behind all of it still is one database, holding every user, every restaurant, every order. Which is where we're going next, because we've spent this whole module making the app tire survivable. 5 machines, any one of which can die without anybody noticing, and every single one of those requests still ends up at that one database, one machine, holding everything. Beat of near silence as everything dims to the lone database. Every request we've traced so far ends in the same place, and we've been drawing it as a plain box at the back of the diagram without ever saying what it actually is. A database is not a special machine. Like the load balancer, it's a program running on an ordinary server. Processor, memory, disk. You could run one on your laptop right now, and plenty of people do. What makes it worth having is that it's built to hold things correctly while thousands of people are reading and writing at the same time. Think about the counter at the front of a restaurant. The kitchen cooks. That's our app servers. But the counter is where the bill is kept, where the money is recorded, where somebody writes down, carefully and permanently, what was actually ordered and what was actually paid. Nobody minds if the kitchen is chaotic. Everybody minds if the bill is wrong. That's the database. So what does Dabba actually keep there? Here's where almost everybody goes wrong. And it's such an easy mistake that it's worth stopping the clock for. The first question people ask is, which database should I use? Postgres or Mongo? That is the wrong first question. Genuinely not. Not there's a better order, but wrong. You cannot choose a database before you know what you're going to ask it. So the actual first question is, what are people going to ask this app to do? Over and over, thousands of times a day. Those are called access patterns. Let's write Dabbas down. Show me restaurants near me, show me one restaurant's menu. Place an order. Show me my past orders, show me the status of the order I'm waiting on right now. Rate a restaurant I ordered from. Look at that list, because it's more than it appears. That is the entire app rewritten as a set of questions. And notice something. 5 of those 6 are reads. Only one of them writes anything. That's the read-heavy shape we worked out on the napkin an hour ago, now staring at us from the data side. Once you have the questions, the data almost designs itself. So the order is questions first, data shape second, technology last. So let's answer those questions with actual data. This step is called data modeling, deciding what you store and how the pieces connect. Start with the obvious ones: a user, an ID, a name, a phone number, an address; a restaurant, an ID, a name, a location, a rating; a dish, an ID, which restaurant it belongs to, a name, a price. Now the interesting one: an order. It has an ID and then it needs to say who ordered and from where. And notice how it does that. It doesn't copy the user's name and address into itself. It just stores the user's ID and the restaurant's ID. That's the pattern the whole model is built on. Every connection between two things is just a pair of IDs. That's why we gave everything an ID in the first place. And a rating: a user ID, a restaurant ID, a score, a timestamp, same shape again. 5 things: users, restaurants, dishes, orders, ratings. That's Dabba's data model. One detail I want to flag now because it comes back and bites us in about 10 minutes: the dish photos. The photo file does not go into the record. The record only keeps a small link that says where the file lives. Why the actual image lives somewhere else entirely is a bigger conversation. Park it. It's coming. And one more thing to be really clear about: none of this is a database choice. We have not picked Postgres or Mongo. A data model just says what we store and how it connects. These 5 things could live in either. Now we can have the argument everyone wants to have first. And now it's easy because we're not guessing, we're reading the answer of our own data model. Look at our dishes. Every single one has exactly the same fields: an ID, a restaurant, a name, a price. That's a table. It practically drew itself. Second, relationships. An SQL database is built to connect tables together. Show me my past orders with the restaurant names means connecting the orders table to the restaurants table. That operation is called a join, and it's what these databases exist to do. Third, transactions. Say someone places an order. You need to record the order, reserve the items, and take the payment. Those 3 things must either all happen or none of them happen. You never want a payment taken for an order that didn't save. Grouping work like that is a transaction, and it's the thing that makes people trust these databases with money. You'll hear the word ACID attached to this. That's the family of guarantees it belongs to. We'll leave it at the name. And that's genuinely useful for data that has no fixed shape. Take how people use Dabba. Which screens they tapped, what they searched, what they scrolled past. Every one of those is different. Forcing that into a fixed table would be miserable. So which one does Dabba get? Read it off the model. Our core data has a fixed shape and it's full of relationships. Orders point at users and restaurants, ratings point at both. Answering our questions means joining them constantly. That's pointing straight at SQL. So the core of Dabba goes in a relational database. We'll say Postgres. But real systems almost always use both. That messy behavior data has no fixed shape and no relationships, so it goes in a NoSQL database alongside. Both connected to the same app servers. The code just knows which one to ask depending on what it needs. It's an if statement, nothing mystical. And if you're ever genuinely unsure, start with SQL. It will carry you much further than people expect. Dabba keeps growing. And one day someone notices that the My Past Orders screen has got slow. Not broken, slow. It used to be instant. Now it takes about 4 seconds. Nothing changed in the code. What changed is that the orders table now has 40 million rows in it. So let's watch what the database actually does when Priya asks for her orders. Row 1, is this Priya's? No. Row 2, is this Priya's? No. Row 3, no. It has to look at every single row because it has no idea where Priya's orders are. 40 million checks to find maybe 12 rows. That's called a full scan, and it's exactly as wasteful as it looks. When the table was small, this was fine. Scanning 10,000 rows is instant. The code didn't get worse. The table got bigger. This is one of the most reliable things that will happen to any system you build. It works fine, then quietly stops working fine, and nothing about it changed except size. No chime. The fix is the next scene. The fix is the same one printed in the back of a textbook. If you want every mention of photosynthesis in a 900-page biology book, you do not read the book. You go to the index at the back, find the word, and it tells you. Pages 12, 97, 340. A database index is exactly that. A separate, sorted structure that maps a value straight to the location of the rows that hold it. So we build an index on the orders table on the which user placed this column. Now when Priya asks for her orders, the database doesn't touch the table at all at first. It goes to the index, finds Priya, and the index says rows 822, 15,000, and a handful of others. Then it jumps straight to exactly those rows. 4 seconds becomes a few milliseconds. And this isn't a toy improvement. One well-documented case took a query on a 500 million row table from 23 seconds down to 2 milliseconds by adding one index. The reason it can do that is that the index is sorted, which means every step throws away half of what's left. Even across millions of rows, you're only ever about 4 or 5 hops from what you want. So, index everything right? Every column? No. And here's why. An index is a promise you have to keep. Every time you write a new order, the database doesn't just add a row, it has to update every index on that table too. More indexes means faster reads and slower writes, and more disk used. That's the trade, and there's no way around it. So the rule is simple, and it's the opposite of what people do. Don't guess. Don't sit down and decide which columns feel important. Ship it, find out which queries are actually slow, and index those. Most tables end up with a handful. 3 to 5, not one on everything. For Dabba, that's who placed the order. And when it was placed, those two answer almost every question we listed. The indexes made every individual question faster, but there's a completely different kind of waste happening. And once you see it, you can't unsee it. Remember what we worked out on the napkin? Dabba is about 100 reads for every write. So let's look at what those reads actually are. It's dinner time. 50,000 people in the same city open the app in the same 20 minutes. And they all ask the same question. What's good near me? Same neighborhood, same restaurants, same answer. And the database works it out from scratch. Every single time. Meanwhile, that answer changes. What? Hourly? A restaurant opens, one goes offline, a rating shifts a decimal. Now, picture the restaurant again. A table asks what's in the biryani. The waiter walks to the kitchen, asks, walks back, tells them. Next table, same question. Off he goes again. Same walk, same answer, 200 times an evening. No restaurant on earth does that. They print the menu once and put a copy on every table. That's a cache. And I want to be precise about what it is, because people think of it as a place. It isn't. A cache is a decision. Don't ask twice. Reading an answer you already have out of memory, instead of working it out again from disk, is routinely 10 to 100 times faster. Not 10%. 10 times at the flow. Hard cut to silence as the waiter stops. So how does it actually work? 3 steps. And this is the pattern behind most of the caching you've ever used. A request comes in. The app asks the cache first. Do you have restaurants near this location? If it does, that's a hit. The answer comes straight back, and the database never even learns the request happened. If it doesn't, That's a miss. Now the app goes to the database, gets the answer the slow way, and on its way back, it drops a copy into the cache so the next person doesn't have to. So notice something uncomfortable. A miss is slower than having no cache at all. You did the whole trip, plus you stopped to write the answer down. Which means this entire idea lives or dies on one number. What fraction of asks are hits? The hit ratio. And when that number gets high, the arithmetic gets silly. Uber runs a cache in front of their databases serving over 40 million reads a second. On one path, 99% of those never touch the database at all. Serving that straight from storage would have needed around 60,000 processor cores. With the cache in front, 3,000. Same answers, 5% of the machines. So what goes in? Not everything. The cache is small and expensive memory, and it's meant to hold the hot stuff. Three properties make something a good candidate. It's small, it's read constantly, and it changes rarely. For Dabba, that's obvious once you say it. The restaurants near me list for each neighborhood. The menu of whichever restaurant is trending tonight. The profile card of a popular place, its name, photo, rating, which barely changes but gets opened thousands of times an hour. And what does not go in? Anything where being slightly out of date causes real damage. The exact status of the order you're waiting on. Anything to do with payment. Now, one thing worth closing a loop on. Remember the shared store we invented in Module 5? The one holding login sessions so any machine could serve any user? That's very often this same thing. The most common tool for both jobs is Redis. Sessions are tiny, read on literally every request, and need to be fast, which is exactly what a cache is good at. So one component quietly doing two jobs. That's very normal. And now the bill. Because the moment you added a cache, you created a second copy of the truth, and two copies of anything can disagree. A restaurant raises the price of a biryani at 4 o'clock. That right goes to the database. The database is now correct. The cache still has the old price. And it will keep confidently handing that old price to every single customer who opens the app. That's stale data. And notice, it's not a crash. Nothing errored. Your system is calmly, efficiently serving the wrong answer, which is genuinely worse, because nobody gets paged for it. There are two tools for this, and you use both. The first is a TTL. Time to live. When you write something into the cache, you attach an expiry. This is good for 60 seconds. After 60 seconds, the cache throws it away. The next request misses, goes to the database, and pulls a fresh copy. It's the lazy fix, and that's not an insult. It's simple, it's automatic, and for most data, it's completely fine. The cost is that you're knowingly serving data that could be up to 60 seconds old. The second tool is active invalidation. When the data changes, you go and delete the cached copy immediately. The restaurant changes the price, and in the same breath, you reach into the cache and throw the old one out. Next request misses, refetches, and everyone sees the new price straight away. More work. You have to remember to do it on every write, but no staleness window. And which do you use? You already answered this back when we asked what Dabba can afford to get wrong. The trending list can be a minute old. Nobody will ever know. Give it a TTL and move on. But whether a restaurant is currently accepting orders, if we're wrong about that, someone pays for food that will never arrive. That one gets invalidated the instant it changes. One last wrinkle, because it's a classic. Say a really popular entry expires. The trending list at dinner time. In that instant, every request that wanted it misses at once, and they all stampede the database together with the identical query. That's a cache stampede. And the standard defense is beautifully petty. Don't give everything the same expiry. Scatter them by a few seconds so the hot entries don't all die at the same moment. And when the cache fills up, because it will, the usual rule for what to throw out is LRU, least recently used. Whatever nobody has asked for in the longest time goes first. Right. Time to deal with the thing we parked twice. The napkin math told us this an hour ago, and we walked straight past it. All of Dabba's order data, every order for a year, is about 18 gigabytes. It fits on a laptop. The dish photos are around 240 gigabytes. The arithmetic told us where the pain would be before we'd drawn a single box. So let's finally fix it. First, photos do not belong in the database. A database is built to hold structured records and answer questions about them. It is not built to hold millions of large files. So you put the files in storage designed for exactly that, usually called object storage, and the database keeps only the small link, which is what we designed for back in Module 6. That one change takes the weight off. It also gets you durability you'd struggle to build yourself. These services are designed to keep multiple copies automatically. Amazon's, for instance, is designed for 11 nines of durability, which is a genuinely absurd number. And a different thing from availability, it means they're extraordinarily unlikely to lose your file, not that you can always reach it. But there's a second problem, and no amount of storage fixes it. Everything we've built lives in one place. And a user in Guwahati is about 2,500 kilometers from Mumbai. Light in fiber moves about 200,000 kilometers a second. That sounds instant, and for one round trip, it nearly is. But remember the home screen. 30 dish photos and 30 separate round trips. 30 trips across the country and back for pictures of biryani. The user waits. And there is nothing you can do to your servers to fix it. Because the problem isn't your servers, it's the distance. So you can't make it faster. You can only make it shorter. You put copies of the photos in cities all over the country. When someone in Guwahati opens Dabba, they get the photos from the nearest one. That network of copies is a CDN, a content delivery network. It's a cache exactly like the one we just built, except it's spread across a map instead of sitting next to your database. Franchise the restaurant, same menu, a kitchen in every neighborhood. And this isn't abstract. One provider alone runs 13 edge locations in Mumbai, 13 more in Delhi, 6 in Telangana, 5 in Chennai, 4 in Bengaluru. Not somewhere in the cloud, a few kilometers from the phone. Second pullback. Look how much of this you can now explain. A request leaves a phone. DNS points it at the load balancer. The load balancer picks a healthy machine from a fleet of stateless servers, any of which can die without anyone noticing, and their login sessions live in a shared store. That machine checks the cache first. If the answer is hot, it never bothers the database at all. If it isn't, it goes to the database, where our indexes mean it jumps straight to the rows it needs instead of reading 40 million. The dish photos aren't in the database at all. They're in object storage, and they're served from an edge location near the user instead of from Mumbai. 11 components. Every one of them added because something specific broke. But look at the very back of the picture. We have 5 app servers so that no single machine's death matters. And behind them, still, is exactly one database, holding every user, every restaurant, every order Dabba has ever taken. If that machine dies at 2 in the morning, and we've already seen a machine do exactly that, Dabba doesn't get slow. Dabba is gone. That's next. Beat of near silence as everything dims to the lone database. One database. Every user, every restaurant, every order Dabba has ever taken. And 2 things are wrong with that picture at the same time. The first is load. Look at the machines. The app servers are coasting at 20% while the database is pinned at 95. Every one of those 100 reads to one write is landing on the same machine. The cache absorbs the hot stuff, but everything else, every past order, every profile, every search that isn't trending, still goes here. The second problem is the one we already know. It's one machine. And a machine is a thing that dies. So we do what we did with the app servers. We stop having one. We keep live copies of the database on other machines. That's replication. The industry standard starting point is 2 copies. So 3 machines in total, all holding the same data. And yes, that triples the bill, but look what we get for it. Because if we're paying for 3 databases, we shouldn't be reading from only one. We spread the reads across all 3 copies. The load on the original drops immediately. And to decide which copy answers each read, we use exactly the same trick as before. A load balancer, the waiter again, this time standing in front of the databases instead of the kitchens. Reads are spread across 3. Now, where do the writes go? And the answer is one place only, the primary. Never the replicas. Here's why, and it's worth 30 seconds because it's the reason the whole arrangement works. Imagine we allowed writes anywhere. A restaurant's price is 240 rupees on all 3 machines. Someone updates it to 260 and that write lands on the primary. At the same moment, a different update sets it to 280. And that one happens to land on a replica. Now which one is true, 260 or 280? There's no answer. Both machines think they're right, and the data has genuinely forked. So, all writes to one machine. That machine is the single source of truth, and the copies follow it. And follow is exactly the right word. The replicas hold an open connection to the primary and stream its changes continuously, which means they are always, unavoidably, a tiny bit behind. That gap has a name: replication lag, usually milliseconds. And the state it puts you in also has a name. The copies are not consistent right now, but they will be shortly. That's eventual consistency. Which sounds harmless, it usually is, except when it isn't. No chime, the bug is the next scene. Priya places an order. That write goes to the primary and it's safely stored. Half a second later, she taps My Orders to check it. That's a read. And reads, as we just arranged, get spread across all 3 copies. This one lands on replica 2. And replica 2 hasn't received her order yet. So Dabba tells Priya she has no recent orders. She just placed one. She watched the confirmation. Now, nothing was lost. Her order is sitting safely in the primary the entire time. The replica was just a few dozen milliseconds behind. But she doesn't know that, and from where she's standing, the app just ate her dinner order. The fix is small and quite elegant. When someone is reading their own recent data, send that read to the primary. Everyone else's reads can go to the replicas. Priya always sees her own order instantly. Some other customer seeing her rating half a second late hurts nobody. And that gives us the opposite term, reading from the primary, where the latest data is guaranteed to be, is strong consistency. But every read you send to the primary puts load back on the primary. The exact load we spread out 10 scenes ago. So you don't make everything strongly consistent. You pick, per piece of data, which parts can tolerate being a moment stale. That decision, honestly, is a large part of the job. Now, the reason we added replicas in the first place, and to explain it, I want to go back to something that happened a long time ago in this video. Remember this. 2:14 in the morning, one machine rebooted for a patch, and Dabba was gone for 6 minutes. We fixed it by running 5 app servers instead of 1. So no single app machine mattered anymore. But we never fixed it for the database. Until now. Watch what happens when the primary dies tonight. The system notices it stopped answering. And then it does something rather good. It picks one of the replicas and promotes it. That replica stops being a copy and becomes the new primary. Writes start flowing to it instead. That promotion is called failover. And the whole thing takes seconds, not minutes. 2:14 in the morning, a machine dies, and this time nobody wakes up. Nobody even notices. That's what replication actually bought us. It spread the reads, yes. But the real prize is that the death of any single database machine is no longer the death of Dabba. Beat of near silence as the timer runs. One warning, and it is genuinely the most dangerous misunderstanding people have about all of this. It's Tuesday afternoon. An engineer on the team is cleaning up test data and runs a delete with a mistake in it. It wipes a million order records off the primary. What do the replicas do? They do their job perfectly. They copy it. Within milliseconds, all three machines are identically, faithfully, correctly empty. Replication protects you from a machine dying. It does not protect you from a mistake because a mistake is just a write, and copying writes is precisely what it's built to do. What protects you from that is a backup, a snapshot of the database taken at a point in time and kept somewhere separate that does not follow the primary. Someone wipes the data on Tuesday afternoon, and you restore Tuesday morning's snapshot. You lose a few hours. You don't lose the company. Replicas are for availability. Backups are for mistakes. They are not the same tool, and having one does not give you the other. Beat of silence on what do the replicas do? Dabba keeps growing, 50 million users now across 40 cities. And a new problem shows up that looks like the old one, but isn't. The orders table has reached 900 gigabytes. It is getting genuinely close to not fitting on one machine. So, add another replica, right? That's what we did last time. No. And this is the single most important distinction in this entire video. So let's be very precise. So if the data doesn't fit on one machine, adding replicas changes nothing at all. Because each new machine has to hold the whole thing too. And there's a second thing replicas don't fix. Every write still goes to exactly one machine, the primary. Spread reads all you like. The write load is untouched, touched. Say it plainly, replicas did not help here. Different problem, different tool. The tool for size and writes is sharding. Instead of every machine holding everything, you split the data and give each machine a slice. No single machine holds it all. Together, they hold everything. Run out of room? Add another slice? But splitting raises an obvious question. Priya opens her orders. Which machine are they on? You can't search all four, that defeats the point. So you pick one field to split by. And that field is called the shard key. For Dabba, the natural one is the user ID. The simplest rule is division. Take the user ID, divide by the number of shards, and the remainder is the shard number. Priya's ID is 10. 10 divided by 4 leaves 2. Priya's data lives on shard 2. Fast, and every server can work it out instantly. But two things go wrong with this, and you should know both. The first is a hot shard. Suppose the 20 most popular restaurants in the country all happen to land on shard 2. Everyone's browsing them all evening. Shard 2 is on fire while the others idle. The fix is a shard key that scatters the popular things instead of grouping them. The second problem is worse. Remember the rule, divide by the number of shards. What happens when we add a fifth? The rule changes from divide by 4 to divide by 5. Priya was 10 divided by 4, remainder 2. Now she's 10 divided by 5, remainder 0. The rule says shard 0. Her data is physically sitting on shard 2. And it's not just Priya. Almost every user's remainder changes. Adding one machine means physically moving nearly all your data between machines. The industry fix for that is called consistent hashing. The details are a topic of their own, but the idea is simple. Arrange things so that the rule doesn't depend on the total number of shards. Add a fifth machine, and it takes over a small range from one neighbor. And everybody else is untouched. This is real, by the way, and it's how the systems you use are built. Instagram bakes the shard number directly into every ID it generates. 8,192 shards worth. Discord moved their messages onto a sharded cluster and watched their read latency at the 99th percentile drop from over 100 milliseconds to 15. One last piece of advice, and it's the one people ignore. Shard as late as you possibly can. Once the data is split, joining it back together is the hardest thing in this video to undo. Beat of silence on replicas did not help here. The reading side of Dabba is now in genuinely good shape. Let's look at the other side. What happens when somebody actually places an order? They tap, and then they wait, and keep waiting. 6.2 seconds. 6 seconds is an eternity on a phone. So what's it doing? 4 jobs, one after another. Charge the card. Tell the restaurant to start cooking. Send the confirmation message. Update the analytics. And the user sits there watching a wheel spin through every single one. Now, one of those genuinely needs the user present. If the payment fails, they have to know right now before the screen says confirmed. But the other 3, nobody is waiting on the analytics update. The restaurant needs to know within seconds, not milliseconds. The message needs to arrive, but not before the screen refreshes. And it gets worse than slow. Watch what happens when the message provider has an outage. The chain is stuck at step 3. The order was paid for. The restaurant was told. And the whole thing fails because a text message didn't send. The customer's money moved and their dinner didn't, all because of the least important step in the list. So how do you take work off someone's path without just dropping it? You write it down and you put it somewhere, it'll get picked up. Picture the pickup counter at a busy takeaway place. When an order's placed, nobody makes the customer stand at the pass while it cooks. It gets written on a slip and dropped on the shelf. The customer's hands are free. They can go. That shelf is a queue. And I'll always call it the takeaway shelf because it's not a bookshelf and it's not storage. It's a place where work sits waiting for someone to pick it up. So Dabba does this. The payment still happens live. That one the user waits for. But the moment it clears, the other 3 jobs get written down and dropped on the shelf. And the app immediately tells the customer, done. 6.2 seconds becomes about 300 milliseconds. Behind the scenes, workers pull parcels off the shelf and do the actual jobs at their own pace, whenever they're free. The side that writes the slip is called the producer. The side that picks it up is the consumer. And the beautiful part is that they never have to meet or even be awake at the same time, which fixes the outage too. The message provider goes down, the parcel just sits on the shelf and gets retried later. The order does not fail. Nobody's dinner depends on a text message anymore. And there's a bonus. Remember the dinner rush? Everyone ordering in the same 20 minutes? The shelf absorbs it. Parcels pile up. The workers keep going at a steady pace. And nothing upstream is blocked. Razorpay handles IPL match traffic jumping from 200 requests a second to 1500 in seconds, partly by doing exactly this. Moving work off the live path. Now something changes as the bug grows. That single event, an order was placed, what it tastes, turns out to matter to more and more people. The restaurant needs to know. The delivery team needs to assign a rider. The customer's receipt has to go out. The loyalty points need adding. The fraud check wants a look. 5 different services, all needing to hear about the same thing. And a takeaway shelf can't do that. A parcel gets taken by one worker, and then it's gone. Hand it to the restaurant service, and the other 4 never hear about it. You could put 5 copies on the shelf, but then the producer has to know all 5 exist, and every time you add a 6th listener, you change the ordering code. So you stop handing it to anyone. You announce it. Picture the expo at the pass shouting, "Table 12, ready." Everybody who's listening hears it at the same moment, and each of them acts on their own. This is publish and subscribe. Pub sub. One side publishes an event to a topic. Every service that subscribes gets its own copy. Reading it doesn't use it up. And the thing that makes it worth it, add a sixth listener next year. A new analytics team, say, and they just subscribe. Nobody changes the ordering code. Nobody even notices. So here's the line worth burning in, because people mix these two up constantly. A queue is a takeaway shelf, one job, one worker, the work gets done once. Pub sub is a call out, one event, and everyone listening hears it. One is for getting a job done, the other is for spreading the news. PhonePe runs about 100 billion events a day through this kind of pipe. But look what's quietly happened to Dabba while we've been fixing things. We started with one program. Now there's an ordering service, a payment service, workers pulling off queues, 5 things, listening for events. A dozen little pieces, each with its own address, which creates 3 problems at once. The phone app has to know where every one of them lives, and if the payments team moves house, every copy of the app on earth has to be told. Second, every one of those services has to check who you are, separately. You log in once, but each service rechecks you. Third, you want one new rule: log everything or slow down anyone hammering us. Where do you even put it? There's no single place. So you stop letting the outside world wander in among your services. You put one door in front of all of them. Picture an apartment society. A dozen different buildings inside, but you don't wander into whichever one you like. There's one gate and one watchman. The phone stops talking to 5 services. It talks to the watchman. One address. And the watchman does the jobs those services were all fumbling separately. He points each request at the right building, checks your pass once at the door, and can even collect several things and hand them back as one bundle. That's an API gateway. Netflix built one for exactly this. They describe it as the front door for every request from every device to their backend. And note what it is not. A load balancer picks between machines that are all the same. Which of these 5 identical kitchens is free? A gateway routes between services that are all different. Which building do you need and are you allowed in? They stack. The gateway decides which service, and a load balancer behind it decides which machine. One more job for the watchman, and it's the one that saves you at 3 in the morning. Somebody's app has a bug in its retry logic. Instead of asking once and giving up, it asks again, and again, and again. 8,000 times a second from one phone. It isn't malicious, it's a mistake. But it will flatten Dabba just as thoroughly as an attack. And everyone else's dinner stops working. So the watchman meters the crowd. And the classic way to do it is simpler than it sounds. Picture a bucket of tokens. Every request needs one token to get in. The bucket refills at a steady rate, some fixed number of tokens per second. Take a request, spend a token. When traffic is normal, there are always tokens and everybody sails through. But when a flood arrives and the bucket runs dry, the next request gets turned away. Politely. 429. Too many requests. Try again shortly. That's a token bucket. And it isn't a toy. Amazon's own gateway works exactly this way. By default, it refills about 10,000 tokens a second and holds a burst of 5,000 for sudden spikes. And crucially, you meter per user. So the one broken app burns through its own bucket and gets throttled, while everybody else is completely unaffected. One honest caveat. Doing this across many gateways at once, when a huge crowd arrives in the same second, gets genuinely hard. That's a deeper problem than we're solving today. And the last trade-off of the whole video, which you may already have spotted. One front door means one place for every rule, and one place that, if it falls, locks everybody out. Same answer as every other time. You never run just one. You run several gateways, with a load balancer in front of them. So, this is Dabba, 16 components, every one of them added, because something specific broke. Now forget all of it. Somebody has just walked up to you and said, build me a food delivery app. Millions of users. Go. We're going to do the whole thing from nothing in about 5 minutes. And I want you to notice something while we do it. You're going to be able to follow every single step. Hard cut to silence on the blank canvas. Hold it. Do not fill it. And we don't start by drawing. We start where we always start. What must it do? Browse restaurants nearby. Place an order. Pay. Track the delivery. Rate it afterwards. That's the whole app in 5 lines, and it took 10 seconds. Now the part that actually decides the architecture. How well must it do it? Browsing has to feel instant. Under 200 milliseconds at the 99th percentile, not the average. Placing an order can take a second or two. People expect that to feel like it's doing something. We can never lose an order or a payment. We can absolutely tolerate a rating being a few seconds stale, and it has to stay up. Call it 99.99%, which we know is about 52 minutes of downtime a year. 5 features, 4 numbers. Everything we build from here has to justify itself against one of those numbers. And if it doesn't go in. Then the arithmetic. And watch how fast this goes now. 100,000 people open it on a given day, twice each, 20 requests a visit. 4 million requests a day. Divided by 86,400 seconds, about 50 a second. It all lands at dinner time. So peak is roughly 10 times that. 500 a second. Order records are about a kilobyte, 50,000 orders a day. 18 gigabytes a year. Nothing. The dish photos are 240 gigabytes, and they get served over and over all evening. 40 seconds. The first time we did this, it took 4 minutes. And the arithmetic is already telling us the same thing it told us then. The orders are trivial, the images are the problem, and the read path is where the whole design will live. Right. Now we draw. 16 components, and every single one gets a reason. Start with the thing that does the work. App servers, a fleet of them, not one, because one machine can't handle the load, and one machine dies. In front of them, DNS, because nobody types IP addresses, they type Dabba.in. And a load balancer, because the moment you have a fleet, somebody has to decide which machine answers, and has to notice when one of them stops answering. Those servers are stateless, so the login sessions live in a shared store every one of them can reach. Because a server that remembers you can't be one of many. In front of the data, a cache. Because 50,000 people ask the identical question in the same 20 minutes, and the answer changes once an hour. Behind it, the database, holding users, restaurants, dishes, orders, and ratings. Relational. Because our data is full of relationships and we need a payment and an order to either both happen or neither. With indexes on it, because scanning 40 million rows to find 12 takes 4 seconds, and looking them up in a sorted structure takes milliseconds. Alongside it, a NoSQL store, because behavior and preference data has no fixed shape and no relationships, and forcing it into a table would be miserable. The dish photos are not in either of those. They are in object storage because a database is built to answer questions about records, not to hold millions of large files. And those photos are served through a CDN because Guwahati is 2,500 kilometers from Mumbai, and no amount of server tuning shortens that. The database gets read replicas because one machine was serving every read, and because it was one machine. And separately, backups, kept away from the cluster because replicas copy your mistakes faithfully and instantly. When the data outgrows a single machine, it gets split into shards because replicas each hold everything, so they help with reads and survival, and not at all with size or writes. Off the ordering path, A queue, because charging the card is the only step the customer has to wait for, and a text message face search failing should never fail an order. And a pub subtopic, because 5 different services all need to know that one order happened, and a queue hands a job to exactly one worker. And at the very front of all of it, an API gateway, because a dozen services shouldn't each be a public address with its own copy of the login check, and because rate limiting has to live in one place. 16 components, and not one of them was a preference. Every one is the answer to a specific thing that broke. Let's send one request through it twice, because the two halves of this app take completely different routes. First, somebody browsing. They open Dabba looking for dinner. DNS turns the name into an address, which points at the gateway. The gateway checks who they are once and passes them through. The load balancer picks a healthy app server. That server checks the cache first. And tonight, this is a hit, so it never touches the database at all. The restaurant photos come from an edge location a few kilometers away, not from Mumbai. Notice what didn't happen. The database was never involved. That's the read path, and that's most of what Dabba does. Now they order. Same front door, gateway, load balancer, app server. But this one writes, it goes to the primary database, not a replica, because it's a write and there's only one place writes go. The payment is charged while the customer waits, because that's the one step where the answer matters right now. And then the app says done. And the other 3 jobs go onto the queue, telling the restaurant, sending the receipt, updating the analytics. The customer is already gone. Meanwhile, the event is announced, and 5 services each pick it up in their own time. 2 paths. One optimized so it barely touches anything. One optimized so the customer waits for exactly one thing and not a millisecond more. And now the honest part, because a design that pretends to be finished is the one that fails. The system is good, it is not done. Here's what it still can't handle. It all lives in one country. A user in London is still far away from everything. And running this across multiple regions is a genuinely hard problem we haven't touched. When the network between 2 parts of the system breaks, you have to choose. Stay consistent or stay available. You can't have both. That trade has a name, the cap theorem, and it deserves its own hour. We showed you that a duplicate request could charge someone twice, and we quietly walked past the fix. Making an operation safe to repeat is called idempotency, and it's the reason double tapping pay doesn't take your money twice. When one service starts failing, everything calling it piles up waiting, and the failure spreads outward. Circuit breakers stop that, and we've built a system with no way to see inside it. Metrics, logs, traces, observability is how you find out something broke before your users tell you. Every one of those is a real gap, and that's normal. This is what a design looks like at this stage. You've solved the problems you have, you know the names of the ones you don't, and you'll add each piece when something forces you to. Which, if you think about it, is exactly what we did for the last 90 minutes. So let's go back to where we started. One server, 800 rupees a month. An app, a database, and some photos, all on the same machine. And that was the right way to start. Everything we added after that came from the same loop, 16 times over. Something broke. We found out why it broke. We added the one component that fixes that specific thing. And then we were honest about what that fix cost us, because every single one of them cost something. That's the whole job. Not memorizing which components exist, you can look those up. Knowing which one your system actually needs next, and what you're giving up to get it. If you want to go deeper on any one of these, every component in this diagram has a full episode on this channel. Load balancers, caching, replication, sharding, queues, gateways, all of it. This was the map. Those are the streets. Thanks for sticking with me for 90 minutes. Go build something and let it break. Then silence. No button, no sting. Let the frame breathe and end.